Hello folks, today we'll continue our discussion of linear transformations, still material from 1.8. Let's recall from last time. The transformation, so just a plain old transformation, I'll write it t goes from Rn to Rm. It's just a rule that assigns to each vector in vector x, let's say in Rn, a unique vector, say t of x in Rm. Okay? So my usual kind of cartoon here is that I start in Rn, and then t allows me to pass over to Rm. I take a vector x that's in Rn, and I get a unique, one and only one vector that sits in Rm. I call it t of x, okay? And we saw last time our kind of most important example of a transformation will be matrix multiplication by, well, let's see. So if I want to input vectors that have n entries, I better have n columns. So it's going to be m by n, matrix A. And let's just do an example. So let me see. Let me take A to be 0, 1, minus 1, 0. So what does this define? This defines this is a 2 by 2 matrix, so it's going to take vectors in R2 and move them over to also vectors in R2. Right, so I've got a couple copies of R2 here. And let's just kind of investigate what this does. So let's do some examples. So I don't know, if I took A times 2, 1, let's say, so 1, 2, 1, that's this vector here. What does it do? So, well, I multiply the matrix times that vector, and I get, it's a vector with 2 coordinates, and the first entry is minus 1 and then 2, right? So it gets sent over to this guy here, okay? And A times, I don't know, let's do another one. I have a different color here, so what if I do minus 1, say? So that's going to be 0, minus 1, 1, 0 times, let's say minus 1, and what does that equal? So now I'm taking this vector here, right, minus 1. I want to make that red, of course. Okay, and where does that go? So that goes to the vector 1, minus 1. So it goes to 1, minus 1 is this guy here. Okay, so, in general, we're taking a vector from Rn to Rm, so we have to have these kind of two different worlds. Often when you, if you have a square matrix, right, that means you're moving from the same dimension, one dimension to the same dimension. You can actually draw it on the same picture. So if this was x, we saw that t of x, or a times x, was this here, right? This was ax. And if this was, say, y, then when we applied a times y, we got this here, right? So this is a times y. So what you're seeing here, hopefully this is enough to convince you that this is just taking a vector and rotating it in the, counterclockwise direction by 90 degrees. So this is actually just rotation in counterclockwise direction by 90 degrees, okay? And so, we'll see this in the future, but we're going to use these matrices to actually provide geometric operations on vectors. So this matrix, just multiplying by this matrix, is actually doing this to the vectors. It's in this case, rotating them by 90 degrees. Okay, so I want to now switch gears a little bit. I want to dig deeper into some of the properties that these transformations have. So let me just note that multiplication, matrix times vector has two important properties that we talked about last time. So maybe I should say, instead of note, I should say kind of recall, because we talked about this last time, that when I take a times, say, x plus y, right? So if I take the sum of two vectors and I multiply it by a matrix, that's the same as taking a times x plus a times y, right? It kind of preserves this addition. And the other property was that if I take a scalar, right, a real number times a vector, and I scale it, and then multiply it by the matrix A, that's the same thing as scaling what I get by taking a times the vector, right? A times the vector is a is a vector itself, and I can scale it by c. So, this is, we talked about this before, that matrix multiplication preserves addition in some sense, or it kind of distributes over addition, and it preserves scaling. Those are the two important properties of vectors. And so this is, kind of inspires a definition now. So let me say it this way. So a transformation, now just any old transformation, I don't think of this as matrix multiplication anymore. A transformation T from Rn to Rm is called linear if it satisfies those two properties. I'll write this out again, I guess, for completeness here, but I'm going to say T of x plus y should equal T of x plus T of y. And this should be for all x, y in Rn, right, the input vectors. And then T of cx should equal C of tx for all real numbers C. Okay? So again, just exactly the same definition. I'm just saying I don't know that this is actually matrix multiplication. This is just the definition of what linear transformation means. So again, if I had to put this in kind of quotes, into a slogan, linear transformations preserve vector addition and scaling. Okay? And what did we just see up here? So we just saw that if you happen to have a transformation that's given by matrix multiplication, it's always linear. So note any transformation that's defined by matrix multiplication is linear. Okay, so for instance, this one that we did with the rotation by 90 degrees, this turns out to be a linear transformation. If you take the sum of two vectors and then rotate it, it'll be the same as rotating each vector and then adding what you get. Okay, and so you can maybe play around with that and check that that works. Let's see, so another thing, another property I want to point out here is that, so let me just say linear transformations satisfy some important properties. And I'll just say this as a fact. So suppose T from Rn to Rm is a linear transformation. Okay, then T of the zero vector always equals the zero vector. So maybe this is part A. Notice that this is a little bit, gotta be a little bit careful because this is the zero vector in Rn, right? And then it spits it over to the zero vector in Rm. So in general, these are actually different vectors. They can have different number of coordinates. And B, the other thing is that T preserves linear combinations. And what do I mean by that? Well, if I take T of a linear transformation, so what does that look like? C1x1 plus C2x2 plus Cn xn. What I'll get there is, basically just applying the rule of linear transformations over and over again, what I'll get is that this is C1 T of x1 plus, C2 T of x2 plus Cn T of xn. So what you get is that, you've inputted a linear transformation here. You get a linear transformation on the right-hand side where the weights are the same as what you had. And, the vectors now are, instead of x1, x2, etc., you have T of x1, T of x2, up through T of xn. So let me actually, just in the remaining time here, let me prove proof of part A. Okay. So let's see. So what do we have to do? We have to show that the zero vector gets sent to the zero vector. So what we're going to do is first note that 0 is equal to the zero vector plus itself, right? This is, This is just a column of zeros, and it's the same as if I take two of them and add together. So what we know is that t of 0 is equal to t of 0 plus 0. And now what we're going to do is we're going to use this linearity property, right? So the linearity property says that when you have the sum of two vectors and you apply a transformation, that's going to be applying the transformation to each one and taking the sum. Okay, and so what we have now is that the t of 0 is equal to t of 0 plus t of 0. At this point, I don't know what t of 0 is, but whatever it is, I can subtract t of 0 on both sides. And so what you get is, well, t of 0 minus t of 0 equals t of 0 plus t of 0 minus t of 0, right? I don't know what this vector is, but I know that whatever it is, when I take away the same vector, this becomes just 0. And this will equal to, well, this goes away because it's the vector minus itself. So what's left here is just t of 0. And that's what we wanted, right? We wanted that t of 0 equals 0. And so that proves our claim. Okay? So again, the linear transformations, we'll see they're very important. They always arise as matrix multiplication, and we'll see in the next lecture that in fact the connection's even stronger than that. So we'll see you then.